Hello students, welcome to section 2.2, polynomial functions of higher degree. In the warm-up, which I would like you to try on your own, it does describe how you can rewrite a function in standard form, sketch the graph, and then state the max or minimum value. We have actually gone through problems similar to this in the past, in the notes in particular and in the homework, wherein you are in fact completing the square. So in your description, please go through that process as you see, and hopefully you'll see again that the answer looks like what you see with the graph as well. Number 2, this is another question that I would like you to solve on your own. So number 2 says, find the equation in standard form of a quadratic function with the vertex at 3, 2 that contains the point 0, 5. So again, keep in mind the language standard form versus vertex form. It's just the nuance of our textbook using this different phrase, which is something in standard form, if we recall, in older textbooks, is ax squared plus bx plus c. In this textbook, it's this. We're typically used to seeing this as vertex form. Anyways, to solve the problem, please do the whole substitution of 3, 2 for h and k, and 0, 5 for x and y. Hopefully you'll see then that it ends up being that vertex form. In other words, standard form. Okay, so graphs of polynomial functions. There is some prerequisite knowledge. You should be able to accurately graph a polynomial function of degree 0, 1, and 2. As we continue, in general, the graph of a polynomial function is continuous and differentiable. This means that it has no breaks, gaps, or holes, or sharp turns for that matter. So if you look at this next problem, A through D, number 1, A through D, determine which of the following graphs represent polynomial functions. So part A is most certainly a polynomial function because, again, there's no breaks, gaps, holes, nor sharp turns. It is both continuous and differentiable, we say. For part B, you can see the curve is what we say continuous. There's no breaks, gaps, holes, or sharp turns. So yes, it's also a polynomial. Letter C is no. There is a break here, or you can even say gap. So no, for sure, it's not a polynomial function. Well, part D, there are 2 sharp turns here. So no, it's not fulfilling the differentiable end of things, but the continuous end of things, it actually does continue. As you can kind of see, there's no definitive break. Although there's sharp turns here and here again, there's no definitive break or stopping point really in this continuous graph. So it's definitely not a polynomial, but it is continuous, not differentiable. The polynomial functions with the simplest graphs are those of the form f of x equals x to the n power. So for number 2, I'm going to ask that you get your calculator out. I want you to look at the graph using y sub 1, y sub 2, and y sub 3 for the following functions for x squared, x to the 4th, and x to the 8th. And do the same as well for x, x to the 3rd, and x to the 5th. Take a moment and do that. Please also, when you're getting ready to set up officially the graph view, set your window for -3 to 3 for both the x and the y direction. What you're going to find is that the parabola x squared here in red is, as you see, inside of that, but in a sense what vertically stretched. You see the blue function x to the 4th, and then stretched one more factor, I guess you could say, x to the 8th power. Okay. So that's how those 3 kind of take shape. And then, of course, off to the right there, we see the same type of thing. Here's x. The blue function is not as stretched out. That's x cubed. Well, the green function is more stretched out than x cubed. So it's actually a stretching concept that we're applying here in context. X cubed, and then x to the 5th. So x to the 5th is more stretched out. If I didn't say that correctly, let me apologize and fix this. X to the 5th is stretched out more than x cubed, which is more stretched out than x, or x to the 1st. Okay, so moving on. The leading coefficient test. It's a pretty simple test. We did have this type of thing pop up in Algebra 2. It's the difference between odd and even degrees, but also when the leading coefficient is positive versus negative, both for odd and for even functions. Now I got to be careful, and I want you to be careful too when interpreting even versus odd degree and the even and odd function analysis, or nature of functions I should say, with the y-axis and origin symmetry that we saw back in a prior section. So in this particular case, a positive leading coefficient, odd degree, goes down and to the left, up and to the right. A negative leading coefficient, odd degree, up and to the left, down and to the right. A good way to remember this is if you reflect back to where, let's just say we're graphing y equals x. The graph of the line y equals x is the graph of a positive slope line. X is just a positive odd degree function. So down and to the left, up and to the right. Every single positive odd degree looks like this, down and to the left, up and to the right. Imagine stretching a line out, or better yet, imagine stretching the cubic out, to form a line. That's the end behavior we say. The notation for end behavior looks like this: as x goes to infinity or off to the right, y or f of x goes up to positive infinity. And as x goes to the left or negative infinity, y goes down to negative infinity. Okay, and I already spoke about this graphically. Well, notice the notation again for the end behavior there. If n is even, so x to the second would be a good example. And if the leading coefficient is positive, look at both arrows are pointing up. Not surprising. So as x goes to the right, y goes up. As x goes to the left, y goes up. And look at the notation. Going to infinity, positive, you have positive infinity there. And as you go to negative infinity here, you go up again to positive. Similarly, but of course, with the leading coefficient now negative, it points down. And again, negative x, I'll just say here, negative y, not positive. Positive x, negative y again. So down and down. As far as an explanation of why it works, frankly, if you just picked another function to observe, I just actually used x to the third here and negative x to the third there, and just really looked at the xy table and just noticed that, as you can see, x getting bigger, y gets bigger, and as x gets smaller, y gets smaller. So as x goes to positive infinity, y goes to positive, and as x goes to negative, y goes to negative. Okay, and again, the graph kind of nicely speaks to that right here as well. Similarly, this right here, same type of deal, except it's negative x to the third. Notice your x's and your y's taking shape. That would then speak to something like this. So again, as x goes to positive infinity, you go down, and as x goes to negative infinity, you go up. This is just an xy table analysis. Determine the end behavior of the graph of each polynomial function. Answers must use appropriate notation. So you can actually do this pretty quickly by looking at the leading coefficient, looking at the exponent, in this case negative and odd, and therefore you know negative and odd is going to go up and to the left, down and to the right, without even knowing everything else on the graph, without even typing it into your calculator. As x goes to positive infinity, y goes down, and as x goes to negative infinity, y goes up. Part B, notice the leading coefficient is positive. The exponent or degree is 2 or even. So again, it's going to go up and to the left, up and to the right. As x goes to positive, y goes to positive infinity. As x goes to negative, y again goes up to positive infinity. Okay, let's continue. On to the next page, clearing up the confusion of roots, zeros, solutions, factors, and x-intercepts. Given that f is a polynomial function and a is a real number, the following statements are equivalent. X equals a is a zero of the function f. X equals a is a solution of the polynomial equation f of x equals 0. X minus a is a factor of the polynomial. A comma 0 is an x-intercept. We will use this information to help us find zeros of a polynomial function. So for number 1, find the zeros of this fifth degree function, of which it's a fifth degree with a negative leading coefficient. So I've denoted off to the right just the end behavior for your information. If you set the function equal to 0, you can see hopefully also you can factor out a GCF of negative 3x cubed. that leads you then to the next step of, as you can see, x squared minus 1 in parentheses. And then the next step, you can see the official factoring of that quadratic. X squared minus 1 is this, x plus 1, x minus 1. And setting this equal to 0, you get 0. This equal to 0, you get negative 1. And lastly, x minus 1, you get 1, setting that equal to 0. So I've denoted that there are 3 real zeros, quite literally. You have this x-intercept, if you were writing it as 0, 0, this negative 1, 1, and this 1, 0. What I've left open here, for a reason, what I've left open is a spot to kind of help us understand why maybe we only see 3 real zeros when technically the degree was 5 in the first place. What we need to see happen when we're doing problems of this nature, we need to see the function have the number of zeros that match the degree, whether they're real or imaginary, if you recall. We're going to get back to that question in a moment. I wanted to continue on though here with number 2. We'll get back to the idea of what zeros possibly remain. Approximate all zeros in relative extrema of this quartic and then sketch the graph. So this quartic is factorable. It factors as x squared minus 1 times x squared minus 1. If you set it equal to 0, this factors as x plus 1, x minus 1, as does the other quadratic. So if this is set equal to 0 and so is that, you get negative 1 twice. And then if that and that are set equal to 0, you get 1 twice. Turns out that these are repeated zeros, we say. And not only those, but so are these two. Okay, and I'll highlight this as our kind of other focal point if we decide upon those two. So we only see, look, negative 1, 0 and 1, 0 on the graph as your quote-unquote x-intercepts. They are also called zeros again, if you recall. However, if you were to look at the factored version of this with the second degree here and the second degree there, we're going to go ahead and denote that as k equals 2. And then again, k equals 2. There's a repeated zero kind of set of principles to stick to. When x minus a to the k is what you have in your final setup as an answer, factors that is, k is greater than 1. So if k is 2, 3, and so on, x equals a is a repeated root with a multiplicity of k, we say. So here we've got 2 and as well here 2. So that is a k equals an even value. So we say that x equals a is a bounce at the x-axis. So negative 1 and 1 are bounce points. It has a multiplicity of 2 at the bounce points. If in fact k were odd, we would see that it crosses the x-axis. And back on this last problem, to fill in the rest of the two answers here, we would say 1, negative 1, and then look, the exponent here is 3, so we would actually count 0. Even though you only see it on the graph once, we would count it a total of 3 times to match the quote-unquote multiplicity here of 3. So it would actually be a, not bounce, but a cross at x equals 0. So again, we count it 3 times. So 1, 2, 3, and then 4, and then 5. So there's actually 3 real zeros, one of which is something that you could write out repeated a total of 3 times. So it's repeated twice, I guess, but you see 0, and then 0, and then 0, and then those two again for a total of 5 zeros. We're going to go ahead and take a look at the next page. Remember that if x equals a is a 0, then x minus a is a factor. We can write each factor, and then of course we can simplify. So if I gave you a problem where I told you the zeros are at 2 and 3, then that tells us that the factor going backwards must be x minus 2. Now I want you to set it equal to 0. Do the same thing with x equals 3. Write it as x minus 3, but set that equal to 0. So if you multiply these two factors in the context of a function, f of x equals that factor times that. If you FOIL this, you'll end up with this quadratic. This is a more typical looking kind of ax squared plus bx plus c form. Otherwise, in other textbooks, of course, we've said standard form. This is a good final answer to this problem, x squared minus 5x plus 6. I do want you to continue on with the next problem. Try it out. It speaks to a nice irrational pair of roots here, of which are conjugates of each other. And I also want you to take a look at the intermediate value theorem as you conclude.